we'll discuss questions from group theory part. This question is appeared in June 2011 CSIR NET examination. Given the character table of the point group C3V with a representation, this symbol is called gamma, which means a representation. Here a reducible representation is given. Listen, A1, A2, E, these are all called irreducible representations. A1, A2, E are called irreducible, and at the bottom, okay, reducible representation gamma is given. Some reducible representation. Some number is given, C630. Now we have to find out the irreducible components. So which means we have to reduce this reducible representation, and we should find out the number of irreducible representation present in this. What I am trying to say, listen, in this point group, this is actually called character table of the point group C3V. In this, A1 is an irreducible representation, IRR, irreducible representation. A2 is an irreducible representation, and this E also an irreducible representation. These are all irreducible representation. Now what we have to do, this is a reducible representation. Now I am going to reduce this. If you reduce it, you will get some number of A1, some number of A2, some number of E. Okay. So this every reducible representation, not only this, every reducible representation is made up of, okay, irreducible representations. Okay. So if you reduce a reducible representation, if you decompose a reducible representation, we will get the irreducible representations present in that reducible representation. Okay. So I'll give the formula for the reduction or for the decomposition of irreducible components. How to decompose the reducible representation. Okay. Listen, this is the formula. AI is equal to 1 by H sigma NR into chi R into chi I. We use a simple formula like this. Okay. Right. Listen, what is meant by this? What is AI here? AI is nothing but number of times the irreducible representation I present in the reducible representation. That's the meaning. Okay. You take some ith irreducible representation and find out how many ith irreducible representation present in the reducible representation. Then what is H? You know very well, H is nothing but order of the group, order of the point group or order of the group. Then NR is nothing but number of operations, number of symmetry operations in the class R. Okay. In each class, how many operations are there? Simple. Then what is chi R? Chi R is nothing but reducible character for reducible representation. Chi symbol indicate character. This chi symbol indicate character. Small r indicate reducible. Character of reducible representation, which is given at the bottom. 630. These are all called reducible characters, right? Characters for reducible representation. And what is chi I? Chi I is nothing but character of irreducible representation. Okay, take note. This is called reduction formula. In this question, 3 irreducible representations are there. In C3V point group, there are 3 irreducible representations. Listen, this is class 1, this is class 2, this is class 3. So we have 3 classes. Identity operation form 1 class. 2 C3, that is C3 and C3 square, they form 1 class. sigma v1, sigma v2, sigma v3. So 3 sigma v, they form another class. So there are 3 classes. Remember, in a character table, number of classes and number of irreducible representation should be equal. In a character table, number of classes and number of irreducible representation should be same. Keep that in mind. Okay. So A1, A2, E, they are all irreducible representations of C3V point group. At the bottom, okay, 630, some characters are given. These are the characters of a reducible representation. Now what we have to do? We should reduce this representation and we should find out how many A1, how many A2, how many E are there in this reducible representation. That is our goal. Okay. Now we'll proceed. Okay, how to calculate this using that formula. I have given the formula. Now I'll show you how to utilize that formula. Okay, right. Observe carefully. Now first let me take A1 representation. So how many times A1 irreducible representation is present in the reducible representation? Okay, summation is there. So we have to add summation. So I am not going to write summation here. Listen carefully. This is the formula. 1 by H. You know very well, for this point group, how many operations are there? 3 plus 2, 5, 5 plus 1, 6. So order of this point group is 6. Take note. Order of this point group is 6. Okay, and in the formula, you know very well, we should put A1 1 by H, no, H is 6, 1 by 6 into summation is there. I am going to sum up, right? I am going to sum up, right? First, I'll take class 1. This is class 1. In class 1, we have only one operation, that is only one identity operation. Number of, this is NR. NR is nothing but number of operation in the class R. So I'll take first class. In this first class, I have only one operation into number of character for the reducible. Character of reducible representation along the class 1. Along the class 1, what is the character? 6. Into character of irreducible. For A1, along A1, below E, see the number, that is nothing but character of irreducible. So this is NR, chi R, chi I. Listen, now in a similar manner, I'll take the class 2. In class 2, we have two operations. Reducible character is 3 and irreducible character along, because we are finding how many times A1 irreducible representation present in the reducible representation. So along A1, you should see numbers. These numbers are called characters of irreducible representation of A1. Okay. So along in class 2, A1 irreducible representation has character 1. So put 1 here, multiply them. Plus, now we should go to class 3. In class 3, we have 3 operations. Then reducible character is 0 and irreducible character along A1, irreducible character is 1. Now, so you multiply these three, then sum up. So 1 by 6 into 1 into 6 into 1 is 6 plus 3 into 2, 6. 3 into 2, 6, 6 plus 6 into 1, 6. Here I have 0, so that becomes 0. 6 plus 6, 12. 12 by 6 is 2. 12 by 6 is 2, right? What does this number implies? This number implies that in the reducible representation, there are 2 A1 irreducible representation present. Okay, A1 irreducible representation. There are 2 A1 irreducible representations present in this reducible representation. That's the meaning. Now, in a similar manner, we need to find out how many A2 present in the irreducible representation. Number of times A2 irreducible representation present in the reducible. We have to proceed in a similar manner. How? See, 1 by order of the group is 6. We have three classes, so I'll put 2 plus symbol. Here I'm going to write class 1, here I'm going to write class 2, here I'm going to write class 3, simple. Only I have, because I have only 3 classes. Now first I'll go to class 1. In class 1 I have only one operation, 1 into reducible character is 6 into irreducible character along A2 we should see, along A2 class 1, irreducible character is 1, plus, then let me go to class 2. In class 2 we have 2 operations, into reducible character is 3 into along A2 irreducible character is 1, plus, then we will move on to class 3. In class 3 we have 3 operations and reducible character is 0. The irreducible character, right, for A2 in class 3 is minus 1, so I'll put minus 1. So what we get here is, what we get here, 1 into 6 into 1 is 6, 3 into 2, 6 into 1 is 6, and here anyway I have 0, so it becomes 0. So 6 plus 6, 12, 12 by 6 is again 2. Okay, can anyone tell me what does this indicate? So far we found out A1 and A2. Now I'm going to find out how many E representation is present, E irreducible representation present in the reducible. Yes, use the same methodology. Okay, number of times the irreducible representation E present in the reducible. So 1 by order of the group is 6, you know. Now there are 3 classes, so this is for class 1, class 2 and class 3. Class 1, class 2, class 3. I am going to sum up. First I'll take class 1. In class 1 we have only one operation, reducible character is 6 and the irreducible character along E is 2. Plus, then go to class 2. In class 2 we have 2 operations, right? 2 operations into along class 2 the reducible character is 3 into along E, along in class 2 the irreducible character is minus 1, plus in class 3 we have 3 operations, reducible character is 0, irreducible character for E also 0. So we get 1 by 6 into 6 into 2 12 plus 3 into 2 6, 6 minus 6 into minus 1, yes it is minus 6 plus 0. 12 minus 6 is 6, 6 by 6 is 1, 6 by 6 is 1. So it implies that the reducible representation, the given reducible representation contains only one E irreducible representation. Okay. Therefore, the given reducible representation is made up of, we found out 2A1 plus 2A2 plus 1 E irreducible representation. Okay. Yes, these are the irreducible components present in the given reducible representation. Okay. So the correct option for this question is option A, option 1. Okay, which consists of 2A1, 2A2 and 1E. Right? Is this clear to all? Okay, this question appeared in June 2013 in the CSIR NET examination. Right? Just go through the question. A molecule contains the following symmetry operations: E, 2C6, 2C3, C2, sigma D and sigma V. The question asked here is number of classes and order of the symmetry point group. Okay, order is very simple, you know. Okay, what is order? Order is nothing but total number of symmetry operations. How many total number of operations are there? Say here I have 3 plus 3 6, 6 plus 1 7, 7 plus 2 9, 9 plus 2 11, 11 plus 1 12. So order of the point group is 12. Okay, but if you analyze the options, in 3 options, option 1, option 2 and option 3, in all these 3 we have number 12. Okay, see, first number is number of classes and second one is order. Okay, so order is 12. So yes, I have 12 here, I have 12 here also, I have 12 here also. So we need to find out number of classes here. Okay, listen carefully. Listen, it is given in a systematic manner, in an easy manner, that they are given directly in class, in classes, right? So identity operation form a separate class. Then C6 and C6 power 5. Remember, C6 and C6 power 5. C6 operation, C6 power 5 operation. They are distinct operation. They form one class. Okay, so which is written as 2CX, 2C6, right? 2C6 form a separate class. So this is class 1. This is class 2. Then in C6, listen, C6 power 2, right, and C6 power 4. C6 power 2 can be written as C3. C6 power 2 can be written as C3 square. C3 and C3 square, they form a separate class, which is written simply as 2C3. Then we have what is called C6 power 3. C6 power, let me write here, C6 power 3. C6 power 3 is nothing but C2. C2 form a separate class. So 2C6, 2C3 form separate class, and C2 form separate class. 3 sigma D form separate class, and 3 sigma V form separate class. Right? In the question itself, they have given clearly, okay, the number of classes also. So here, how many classes are there? 1, 2, 3, 4, 5, and 6 classes. Yes. So number of classes equal to 6. So the correct option for this question is option number 3. Okay, take note. This is the next question. This question appeared in 2019 June CSIR NET examination. The question is this: the number of times A1 representation, A1 is nothing but irreducible. The number of times A1 irreducible representation appears in the representation given here. There is some representation given here. In this representation, how many A1 is there? Okay, just use the reduction formula. Yes, just use the reduction formula and find out number of A1. Isn't C2V character is supposed to be given? Yes, in the question paper it was there, but purposefully I didn't give here. Right? Listen. For C2V you can write easily. Okay, the C2V character table is very easy. Just remember this. C2V character table I will write here. It has identity operation, C2Z, sigma vertical XZ, then sigma vertical YZ. Observe carefully. It has four classes. 1, 2, 3, 4 classes. Therefore, there should be 4 irreducible representations. What are they? A1, A2, B1, B2. There are 4 irreducible representations. What are the characters? Characters of the irreducible representation. Observe carefully. For C2V, we can write, okay, in our own. Okay, for C2V, character table is not necessary at all. It is easy to write. How? First row you put 1, 1, 1. Okay. Listen, if all the characters are plus 1, for an irreducible representation, that irreducible representation is called totally symmetric irreducible representation. Totally symmetric irreducible representation. I'll write simply IRR. Listen, in any character table, for a particular irreducible representation, if all the characters are plus 1, then that irreducible representation is called as totally symmetric irreducible representation. Okay, keep this in mind. So now for C2V, you write the first row as 1, 1, 1 and the first column also 1, 1, 1. Then leading diagonal also 1, 1, 1 plus 1. First row plus 1, 1, first column plus 1, 1, leading diagonal plus 1, 1. Remaining places you put minus 1. In remaining places you just put minus 1. Yes, this is the character table for C2V. Take them. Actually.
Yes, sir.
Yeah, listen. So use the reduction formula. Number of times ith irreducible representation present in the reducible representation is equal to 1 by h sigma nr into chi r into chi I. This is the formula. Now in this case we need to find out how many A1 irreducible representation exist. So in the place of I you put A1 1 by, and for this point group there are 4 symmetry operations available, 4 classes, 1 2 3 4 classes and 4 symmetry operations. So order of the point group is 4. Order is nothing but total number of symmetry operations. So we have totally 4 here, so order is 4. Then since there are 4 classes, okay, so this is for class 1, this is for class 2, this is for class 3 and this one is for class 4. So we need to add 4 terms. Term 1, first take class 1. In class 1 we have 1 operation and class 1 reducible character is 3. In class 1 irreducible character for A1 is 1. Remember we need to find out A1 alone in this problem. So don't worry about A2, B1, B2 and all. Okay, just A1. For A1 irreducible character is 1 plus. Then go to class 2. We have 1 operation, or I can see here. So we have 1 operation in class 2, 1. Reducible character is 1. And along A1, class 2, irreducible character is 1. Plus, in a similar manner, go to class 3. In class 3, we have only 1 operation. 1 into reducible character is 1. And corresponding irreducible character for class 3 along A1 is 1. Plus the next class is sigma v prime or sigma v yz. Number of operation is 1. Reducible character is 3 and the corresponding irreducible character of A1 is 1. Okay, so now you multiply. 1 into 3 is 3, 3 into 1 again 3. So 3 plus 1 into 1 into 1 is 1 plus 1 plus 3. What we get is 3 plus 1 4, 5, 5 plus 3 is 8. 8 by 4 is 2. So what does it indicate? It indicates that this reducible representation contains 2 A1 irreducible representations. Okay, take note. Therefore, the correct option for this question is option 2 or option B. Okay, so this is our next question. The E into E direct product in D3 point group contains irreducible representations, right? Irreducible representations are given here. You need to find out, okay, the direct product E into E here. Okay, and we need to find out what are the irreducible components present in E into E. Okay, yes, what is meant by that? Listen. Okay, listen, this is regarding direct product. Direct product. Listen, we represent direct product by this symbol actually. Actually, it is given cross. They are supposed to give a circle with a cross. This is the standard representation of direct product. If you take direct product of, right, 2 irreducible representation and another irreducible representation, what will be the result? Listen carefully. Point number 1. If I take a one-dimensional irreducible representation, one-dimensional irreducible representation, and if I multiply this with another one-dimensional irreducible representation, and so I am taking direct product of okay, 2 one-dimensional irreducible representations. The answer is also a one-dimensional irreducible representation. If you take direct product of 2 one-dimensional irreducible representation, your answer also one-dimensional. Point number 2. if I take direct product of a one-dimensional irreducible representation with a 2 or 3-dimensional, okay, right? Suppose I'll just multiply this with a 2-dimensional irreducible representation. What will happen? Listen, this is 1 anyway. 1 into 2 is 2. So the answer is 2-dimensional irreducible representation. If I multiply a 1-dimensional irreducible representation with a 3-dimensional irreducible representation, okay, 1 into 3 is 3. So I'll get 3-dimensional irreducible representation as a result. Take note. If I multiply a 2-dimensional irreducible representation with a 2 or 3, right, another 2-dimensional irreducible representation, okay, then the result may or may not be an irreducible representation. Usually it end up with a reducible representation. Take note. If you multiply a 2-dimensional irreducible representation with another 2-dimension, okay, you will end up with a reducible representation. Take note. If the irreducible representations given as symbols A and B, we call them as one-dimensional irreducible representation. Okay, in a character table, if you find symbol A or symbol B, then they are one-dimensional. If you see E symbol, then it is called two-dimensional. If you see F symbol, or sometime in some book F, instead of F they'll give T symbol, it is called three-dimensional representation. Take note. So in this question they are asking the direct product of E into E. Now you know E means 2-dimension. So here we are taking direct product of, okay, a 2-dimension with another 2-dimension. Therefore we know very well the result should be reducible. Okay, now listen carefully. What are the characters of E given? See, what are the characters of E in the character table? 2, right? Let me write here. This E is the irreducible representation, right? And what are the symmetry operations given? E, 2C3, 3C2. These are the symmetry operations. Observe carefully. For E, okay, this is actually E, and number 2 is actually typo error. Let me write E. E, along E, identity operation as character 2, class 2 as character -1, and in class 3 the character is 0. These are the irreducible characters of E. Now you take another E, because we are going to multiply E and E. So you take another E, 2, -1, 0. Multiply them. 2 into 2, 4. -1 into -1 is +1. 0 into 0, 0. So this is E cross E. This is the direct product of E and E. Take note. So here, this is, if you take the square of this character and if you add them, you will get that value is greater than the order of the group. Okay, what is the order of the group? Order of the group is 3 plus 2, 5, 5 plus 1, 6. So if you add roughly, if you take square of these numbers, if you add them, you will get 17, which is greater than 6, which means this is a reducible representation. Whenever we get reducible representation, we have to reduce it. And we should find out how many A1, how many A2, how many E are there. Okay? Yes, they are asking that information only. Okay, so what I'm going to do, listen. First I'll find out A1. Okay, yeah, listen. So how many times A1 is present? A1, okay. Order of the group is 6, so 1 by 6. There are 3 classes. So 1, 2, and 3. There are 3 classes. First I'll go to class 1. In class 1 I have one operation. Reducible character. This is the reducible character now. Reducible character is 4. And for A1, along in class 1, irreducible character is 1. Plus class 2, number of operations 2. Reducible character is 1. Along A1, in class 2 we have 1, plus in class 3 we have 3 operations, right? And reducible character is 0, irreducible character is 1. So what's the answer? 1 by 6 into 4. This is 4 plus 2 into 1 into 1, 2, and this is 0. So 4 plus 2, 6, 6 by 6 is 1. Okay, so we are getting 1A1. Once I get the answer, I'll check it. Where we have 1A1. Which is the answer?
Option 1, sir.
This is the next question, which appeared in 2011 June. Okay, this is actually an application of group theory in spectroscopy. Okay, a character table for C3b is given and a reducible representation also given here. For which of the following transition is forbidden? Right? 4 options are given: A1 to A1, A1 to E, A2 to E, A1 to A2. Among the 4, which is a forbidden transition, we need to find out. Take down. So in this question, we need to find out, right, among the 4, which transition is forbidden. We need to find out which is forbidden, symmetrically forbidden. Okay, yes, how to check it? So first I'll take option 1, A1 to A1, right? Whether A1 to A1 is allowed or forbidden, how to check? So let me take option 1. Okay, that is A1 to A1 transition. Listen, while writing symbols, Mulliken symbols for molecules or in transition, we write small symbol, small a1. But in the character table, those symbols are actually capital A1. So instead of small a1, you put capital A1. While writing for molecular orbitals, for electronic transition, okay, we use small symbols, small letters. But in the character table, the corresponding irreducible representations are given as capital A symbols. Now, so what is the question? The question is whether A1 to A1 is allowed or not. What to do? You just take the direct product of A1 into A1. Okay, so A1 characters, listen, 1, 1, 1, 1. Let me write here 1, 1, 1, 1, A1 characters. Again, you take A1, 1, 1, 1, 1. You multiply them, 1 into 1, 1, 1, 1, 1. Okay, 1, 1, 1, 1. This is actually the character of A1 again, correct? Am I right? Listen, so here we have, I made a mistake. So along A1 we have 1, 1, 1, 1. Okay, so let me take 1, 1, 1. And again here A1, another A1, 1, 1, 1, 1. You multiply the characters. So you'll get 1 into 1 into 1, 1 into 1 into 1, 1. So I am getting again A1. What is meant by this? A1 cross A1 is A1. Okay, our direct product of 2A1 is A1. Now along A1, see the third column. This is our third area. Okay, this is area 1 of the character table, and this is called area 2. This is area 3, and this is area 4. A character table has 4 areas. Along area 3, right, and along A1, you just check whether X or Y or Z present or not. Right, now along A1, I have Z. I have Z. Z means you just write mu Z. Okay, it has a dipole moment, right, along Z direction. If X or Y or Z exist, then that transition is an allowed transition. Okay, take note. Now we'll see the second option, because we need to find out which is forbidden. So let me take the second option. In second option, I have A1 to E. I have A1 to E. E. A1 means you just put capital A1, and for E you put capital E. Now this transition is forbidden or allowed, we have to check it. So I am going to take the direct product of A1 into E. I know very well A1 is 1 dimension, E is 2 dimension. So 1 into 2 is 2. 1 into 2 is 2. I am going to get irreducible because this is irreducible, this is also irreducible. If I multiply a one-dimensional irreducible with a two-dimensional irreducible, I will get two-dimensional irreducible. Okay. So, what are the characters of A1? 1, 1, 1. See the table. 1, 1, 1. What are the characters of E? 2, minus 1, 0. 2, minus 1, 0. Just multiply them. 1 into 2, 2, minus 1, 0. 2 minus 1, 0 is the answer, and this corresponds to, again, E reducible representation. So, A1 into E is E. Now, along E, you see area 3. In area 3, I have X as well as Y. Okay. So, A1 to, or along E, along E, I have X as well as Y. Therefore, this transition is also allowed. Take down. Here, A2, the third option, it is given as A2 to E. So, you take capital A2, capital E. Okay, whether A2 to E allowed or not, how to check? Take the direct product of A2 and E. Okay, A2 characters are, in the character table you check it. Characters of A2 are 1, 1, minus 1. And characters of E are 2, minus 1, 0. Now, direct product means you have to multiply the characters. So, 1 into 2, 2. 1 into minus 1, minus 1. Minus 1 into 0 is 0. 2, minus 1, 0. These are the characters. These characters corresponds to E again. They are E. So, which means A2 into E is equal to E. Along E, in area 3, we have X as well as Y. It means this transition is also an allowed transition. Okay, take down. We need to check the last option, that is A1 to A2, whether it is allowed or not. A1 means you take the capital A1. For A2, you take capital A2, and we need to check whether this is allowed or not. So, you take the direct product of A1 into A2. Yes, anyone tell me what is the direct product of A1 to A2 here? See, since A1 is totally symmetric, if you multiply any irreducible representation with totally symmetric irreducible representation, you will get the same answer. Whatever irreducible representation you multiply, you will get the same. If you want, you can also check like this. A1 characters are 1, 1, 1 here. A2 characters are 1, 1, minus 1. So, if I multiply, I will get 1 into minus 1. So, A1 into A2 equal to A2 again. Now, you see the character table. Along A2, is there any X, Y, Z exists? Don't see RX, RY, RZ. Okay, just to see X, Y, Z. So, in the character table under area 3, there is no X, there is no Y, there is no Z. Which means A1 to A2 transition is forbidden, symmetrically forbidden. Okay, or electric dipole forbidden. I repeat, this transition is electric dipole forbidden. Take down. Important. See, in this case, we have found out that A1 to A2, okay, A1 to A2 is allowed or not. We found out how we took the direct product of A1 and A2, which is equal to A2, and along A2, in area 3 of the character table, there is no X, no Y, no Z, nothing is there. So, we said that the transition is forbidden. Yes, our answer is correct. Okay, but I need to give some more information here. If you check only X, Y, Z, okay, then it is forbidden. How it is forbidden? It is electric dipole forbidden transition. Electric dipole forbidden. Okay. But see here, the direct product of A1 into A2 equal to A2. Along A2, you check whether Rx, Ry, Rz exists or not. Is anyone exist? Yeah. So along A2 in the character table, we have Rz, which means the same transition is magnetically allowed. This magnetic dipole allowed transition. Magnetic dipole allowed. Okay, so remember, this is very important information. A transition may be electric dipole forbidden, but the same transition may be magnetic dipole allowed. What does this indicate? Listen, if a transition is electric dipole, suppose if a transition is electric dipole allowed, you will get intense peak. If a transition is electric dipole forbidden but magnetically allowed, means you will get a low intense signal. Okay, if a transition is, suppose if a transition is electric dipole allowed, you will get an intense signal. But in our case, the transition is electric dipole forbidden but magnetic dipole allowed. Magnetic dipole allowed means you will get a signal with a small intensity or lesser intensity. Okay, take down. Is this clear to all?